So we talk about another thing. So this is the Platonic solids. Okay, so Platonic solids comes from what? Comes from Plato. So Plato is the great philosopher. It's Greek, right? A long time ago. And then at that time, people discovered that there are certain kind of shapes, 3D shapes, that are very regular. So regular in a sense that, so in this solid, each face each of the face is a regular polygon. It's a regular polygon. And all the faces are the same. All the faces are the same shape. The same in size or in everything. And so what are the examples? So for instance, if you look at the cube, so this is the cube. Is that okay? So a cube is made up of square in each of the surface, right? And there are 6 of them joining together. Each one of the face is a square, and they are doing the same square. Okay, so this is an example. And there is another example. So if you start by using an equilateral triangle, then you have this tetrahedron. So tetrahedron is another form of this kind of Platonic solids, because each face is an equilateral triangle. They have the same side on each one, and then what? And then there are 4 faces, and then each face is also an equilateral triangle of the same shape. There are others. So for instance, imagine there is a pyramid. So what is a pyramid? So a pyramid is you have a square base. So you start with a square base, and then you have a vertex here that joins to each face. Now, each one of them is an equilateral triangle, but this is not Platonic solid. It is because the bottom part is not the same shape as the other one. It is a square rather than an equilateral triangle. But imagine if you put 2 pyramids together. So if I put another pyramid here, is that okay? Then this becomes something with 8-sided. So we call this octahedron. So oct means 8, right? Well, let me ask you. So October is 10th is the 10th month. But why do we call it October rather than? Yeah, why don't we use? So what's the reason? Do you know? Anyone knows the reason why October? So what is the relation that October to 8? If you know, if you have heard of this one before, could you please raise your hand? Okay, what's the reason? Can you try? 用中文。对，为什么 ？OK， so 为什么就是10月我们把它叫 October？ Okay, very good. So it's because at the Rome Empire, okay, October is really the 8th month. Okay, it's really the 8th month. They start each calendar year in March. So March is the 1st month, and then October is the 8th. So November is the 9th one. So November is related to 9. So nonagon is a polygon that has 9-sided. Decagon is a polygon that has 10-sided. Or we are using the decimal system, right? 十进位 decimal system. So it is the 10th month. Okay. And then just some. So what is July? So July comes from what? July comes from a person called Julius Caesar. Okay, so Julius Caesar is a very great emperor at that time. So he declared that this month, I guess this is the month that he is born. Okay, that we call it July. Okay, and then his successor later is called Augustus Caesar. Okay, and then what? Okay, he named the month August. So I'm not sure whether he picked this by random or this is the month that he was born, but it is August. And there are some interesting things you can check from the Wikipedia, but this is what I know, okay, what I remembered. So February is the month that people doesn't like. People they don't like because it is the time, it is the last month of the year, and then there are a lot of executions. So people get killed at that time. So they don't like February. So originally each month at that time, if my memory is correct, there are 30 days in each month. Okay, but because Julius Caesar says that, oh, I'm very great, okay, so I should have 31 days. So he picked one day from February to July. And then Augustus Caesar says, oh, okay, I cannot be that bad. Okay, so I should also have one day. So he takes another day. So that's why February now has fewer number of days than the other month. Okay, but okay, so that's enough. Okay, so this is octahedron. Okay, so this is tetrahedron. Tetra means 4. Tetrahedron. And then this is octahedron. And actually, I've brought some model here with me. So okay, so this is the standard cube. Is that okay? So this is the standard cube. There are 6 faces. This is the tetrahedron. Okay, let me see. And this is the octahedron. So octahedron, this is very interesting. Okay. Things are very regular. So if you look at this side, these are the same 4 equilateral triangle joining to each other. So if you think of this as there is a square base here, there is a square that joins 2 pyramids to each other. You rotate this by any angle. You change the top and the bottom, then this is also a square. So it is like if you look at the cross section here, you cut here, you see a square. But you change it, you cut it in another direction, then you also see a square. It joining these two together. So this is the octahedron. And then we also have this one. This is called the dodecahedron. Dodeca. So there is deca means 12, right? Deca means 10. Dodeca means 12. So this is called the dodecahedron. So this is made up of what? Pentagon on each surface. Is that okay? A regular pentagon on each surface. They have the same size, and each pentagon is the same. And then this is a dodecahedron. So you have one. There is a pentagon here. Each one joining 1, 2, 3, 4, 5. Each one joining 1. So there are 6 of them, white, and on the opposite side there are 6 red. So you can count it. So there are 12 of them. And then this one you can make it by yourself. Okay, so you can find 2 very hard paper. So like what I'm using, a red one and a white one. You cut them out, you fold it, and then find the rubber band. Okay, you can find the rubber band that goes across this one, and then it will pop up and then becomes this one. But for this one, yeah, it's not very. Do you understand what I'm talking about? Okay, so what you can make a shape, a dodecahedron, without using any glue. This is what I'm trying to say. So you have a pentagon. You have another pentagon. Another pentagon. Another pentagon. Whatever. Okay, pentagon. And then another pentagon. Okay, so you have 2 pieces of this. You have 2 pieces of this. So there is one that you are putting at the bottom, okay, and then you find a rubber band. You find a rubber band. So let's say this is a rubber band. You join this one, 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 this one. Okay, you put the rubber band around these 2, and then it will pop up and then becomes something like this. So this is some fun game that you can try it at home. So this is the dodecahedron. And there is one more. I forget. I forget the name. I think this is, yeah, you can check. Okay. So this is the 20 faces polygon. Okay, I forget the name. Okay, but this is there are 20 faces. So if you look at it, each face is a regular triangle, equilateral triangle, and there are altogether 20 faces of it. So how do you count? If you look at it, there are 5. Am I correct? So there are 5 here. So 1, 2, 3, 4, 5, and then the bottom is also 1, 2, 3, 4, 5. Is that okay? And then for each edge here, the 5, this is an edge in the top, this is an edge in the bottom 5. It goes with a different triangle. So there's 10 in the middle ring, 5 on top, 5 at the bottom, and 10 in the middle. And so there are altogether 20 faces here. And all of these things they're regular. So they are symmetric in each direction. You can change this like this. It looks the same as if you change this like this. Is that okay? Is that okay? Good. And then there are, so amazingly, so for all the years, okay, these are the only 5 Platonic solids that people know. There are no 6. There is no 7. People try to come up with, do we have other Platonic solid? But there's no. Okay. Now notice that we count it as a Platonic solid. We require that every face should have the same shape. If you allow that there is some change in the face, or if you allow some change in the regularity of each polygon, then you can have other solids, like a football. So you can have a football that made up of hexagons and pentagons. Is that okay? But here, what we are doing here is we are saying that all the faces should have the same polygon. But if we have this kind of requirement, then there are just 5. So nobody knows the reason until when? Until we have the Euler planar formula. Euler planar formula helps us to show that these are the only 5 Platonic solids in the whole universe. Okay, you cannot have the 6th one. Is that okay? So today we are going to look at how we can use Euler planar formula to show this is true. And then it is simply by counting. It's not difficult. Okay, so why is it related to Euler planar formula? So if you look at each of these objects, look at each of these objects, each of these corner points, you can think of this as a vertex, and each of these edge, there's an edge that is joining 2 vertices. Is that okay? Then you can imagine making one of these one. So think of this as a net, as a fishing net that is elastic. You can make it long or make it short. Okay. So you make the one you choose. You can pick one of the surface, make it very, 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 very large. When it is very okay, so let's choose this as the surface. You can make it very, 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 very large because it looks like a fishing net. You can make it very large, and then you press everything onto the table. That this becomes a graph, and this becomes a planar graph. Is that okay? It is just like you have a. So this is a. So we have done this before. This is a cube. You can make this very, very large. You can make these 4 edges very, very large. Very, very large becomes something like this. Very, very large. And then what is the other edges inside? It becomes something like this. Okay. It becomes something like this. Am I correct? Once it becomes very, very large, it looks like this, and then you press everything on the table. And then you should have no edge crossing each other. Okay. Actually, anything, any graph that you can draw it on the ball. Okay. So you can do something like this, make it very, very large, and press it. Okay. So it becomes planar. So all the Platonic solids that we can imagine, they are planar graphs. Is that okay? Imagine each corner as a vertex, then it is a planar graph. So we are going to make use of this connection. Okay, a Platonic solid is a planar graph to show that there are only 5 Platonic solids, all that we have already seen. Okay. So let us recall what is the Euler planar formula. So the Euler planar formula is this one, V plus F is equal to E plus 2. Is that okay? So my memory, very famous Euler. Yeah, okay, so this is, okay, V plus F is equal to E plus 2. Okay, and then let's check out the relationship of a Platonic solid with this formula. Okay, so we are going to use this. Okay, so first of all, let me define two extra notation. So I'm going to define n, and then I'm going to define m. Okay. So m is the degree of each vertex in the Platonic solid. M is the degree of each vertex in the Platonic solid. So if you look at this, this is a cube. For each vertex here, it is joined to 1, 2, 3, 3 edges. So in this case, the degree is 3. Is that okay? How about this one? This is a octahedron, right? So for each vertex, it is joined to 1, 2, 3, 4. So the degree of each vertex here is 4. Notice that it is regular. So the degree of any vertex must be the same. It's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Is that okay? And then for this one, this is a dodecahedron, 12. So this you can make it a calendar, okay, of a year calendar. So you can place the dates on each month here. 1, 2, 3. There are 12 faces, okay. And here, for this, each of these vertices, it is 1, 2, 3. It is 3. Is that okay? So it is not always 3 or 4. But if you look at it, there's 5. Is that okay? So this vertex is joined to 1, 2, 3, 4, 5. Is that okay? So m is the degree of each vertex. And then n is the number of sides in each polygon. Of each polygon. Okay, so first of all, n needs to be, so there are something that we should know. N should be greater than or equal to 2. No, not greater than or equal to 2, greater than or equal to 3. Is that okay? Because the smallest polygon has 3 sides. It is a triangle. 2 sides you cannot make a polygon. And similarly, the degree of each vertex has to be greater than or equal to 3. Is that okay? So imagine if you have a corner point that just has 2 edges, then you cannot make a 3D shape. It's just like you're gluing 2 pieces of papers together. Is that okay? So to have a corner, you need to have at least 3 edges joined into it. 2 edges, you cannot make a corner in 3D. Okay? So we have these things. Okay, now let us do some counting. So we want to show if you have a graph that represents a Platonic solid, what properties it will have. So we will let V to be the number of vertices, E to be the number of edges, F to be the number of faces, N to be the number of sides on each polygon, and then M to be the degree. So first of all, we have this handshaking theorem here. So we have N times F must be equal to 2 times E. Okay, so what I'm saying, okay. So let's take a look of this. This is the cube. Is that okay? It is the cube. Okay, this is the cube. So N times F means what? So I have 6 faces here. 6 faces for this polygon, for this cube. And then for each face, there is 4 sides, 4. I'm saying that 4 times 6 will be equal to 2 times the number of edges in this polygon. So the reason is that, so let's do some simple counting. So how do I get N times F? So I get 1, 2, 3, 4. So for this face 1, I get 1, 2, 3, 4 for this phase 2. And then I get 1, 2, 3, 4 for this phase 3. And so on and so forth. I get 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 for each of the phase. So if I get all of the 6 phases, I should get 4 times 6 number of edges in total. If you understand what I'm doing here so far, could you please raise your hand? Okay. Now, very good. But now, if you look at each particular edge, let's focus on this edge. It is used twice. One in counting this phase, and the other time counting this phase. Is that okay? Each edge is counted twice. So it is like the handshaking theorem. Is that okay? So when we are doing these operations, each edge is counted twice. So 4 times 6 must be equal to 2 times the number of edges here. So in this case, if you look at it, if you count the number of edges, the number of edges turns out to be 12. There are 12 edges here. Is that okay? So this is just this example for this solid. For any Platonic solid, we must obey n times f must be equal to 2 times e. Is that okay? Is that okay? Good. Good. Now, again, we use the same idea. We have v times m is equal to 2 times e. What is v times m? So v is the number of vertices. So let's do this time let's use a tetrahedron here. This is the tetrahedron. Actually, a tetrahedron is a K4. A tetrahedron is actually a K4. You have 4 vertices, and then each pair of vertices joining with an edge. So it is a K4. Now you have a tetrahedron. You look at each of the vertex here, and then you are counting its degree. 1, 2, 3, and then this vertex 1, 2, 3. This vertex 1, 2, 3. This vertex 1, 2, 3. Is that okay? So it is actually the handshaking lemma, exactly the original handshaking lemma. Each vertex has degree m. So this is the total degree. The total degree of all the vertices must be equal to 2 times e. Is that okay? If you are okay with this, could you please raise your hand? Excellent. Okay, good. So now we can substitute this n and vm into the original formula. Okay, so what do we have? M is equal to v is equal to m 2e over m. So we have what? We have 2e over m. So let's compare this with the Euler formula over there. V we can change it to 2e over m. F you can change it to 2e over n. Is that okay? And then it is equal to e plus 2. Is that okay? And we can divide each side. So this is by the Euler planar formula. So we can divide 2e on both sides. You get 1 over m plus 1 over n is equal to 1 over 2 plus 1 over e. Okay? If you are okay with this so far, could you please raise your hand? Okay, good. And then, okay, m and n are integers. And then we need to get equality. We need to get equality on both sides. So the first claim is that one of these m and n has to be equal to 3. This is my claim. One of these, okay, so this is the first claim. At least one of the mn is equal to 3. So this is my first claim. Okay, why? Why? Okay, so we can prove this by contradiction. So if it is not equal to 3, if none of them is equal to 3, what will happen? None of them is equal to 3, what will happen? So this one will be greater than or equal to 4. This one will also be greater than or equal to 4. Is that okay? Because if no mn is equal to 3, then both of them must be greater than or equal to 4. Is that okay? But 1 over 4 plus 1 over 4 is at most 1 over 2. But on the right-hand side, it's at least 1 over 2. So it cannot be true. Does that make sense? Does that make sense? So what we are claiming, m has to be 3 or n has to be 3. If both of them is not equal to 3, then the left-hand side must be smaller than or equal to 1 over 2. Is that okay? Okay? Okay, just put in the figures. If m is not equal to 3, maybe it is equal to 5. Okay? And n is not equal to 3, maybe it is equal to 4. Okay, maybe it's like this. But 1 over 5 plus 1 over 4 is very, very small. It is not even close to 1 over 2. But the right-hand side, it is already 1 over 2. Is that okay? So it can't be true. So if it is 5, it is 4, it is not okay. How about 4, 4? If it is 4, it is 4, then 1 over 4 plus 1 over 4 is just equal to 1 over 2. So they cannot be equal. Okay, so in that case, these m and n cannot both be very large. One of them has to be equal to 3. If you are okay with this, could you please raise your hand? Okay, excellent. So how many cases are there? So one of them is equal to 3. So let's draw a table. So let's draw a table about this m and n. So m and n, okay? So let's say m is equal to 3, then n may be equal to 3. Is that okay? Let's say m is equal to 3, then n may be equal to 4. Let's say m is equal to 3, n may be equal to 5. Is that okay? Maybe. I don't know. How about this one? Can I have 3 and 6? Now we can't have 3 and 6 because 1 over 3 plus 1 over 6 is only 1 over 2. So it is not large enough to be equal to the right-hand side. So you can't have 3, 6 here. Is that okay? If one side is 1 over 3, the other side, it hits at most 1 over 5 rather than 1 over 6. Is that okay? So you can have 3, 6. So that's the end. So for the case of m is equal to 3. So when n is equal to 3, then m can be equal to 3, m can be equal to 4. When n is equal to 3, then n can be equal to 5. And again, when n is equal to 3, m cannot be equal to 6 or any number that is larger because this formula does not balance. Okay? Is that okay? So that means that if there is a Platonic solid, it must be either one of these cases. You can't have any other case. And then every one of them, you have a match. So we have exactly 5 Platonic solids in the whole universe. So this is what? Triangle. And then each one has degree 3. So this is a what? This is a, it's made up of a triangle. Each one has degree 3. So this is a tetrahedron. Very good. And how about this? This is n is equal to 4. This is a square. And then each corner is joined to 3 edges. So what is it? This is a cube. This is a regular cube. This is each side. Each polygon has 5 sides. So it is a pentagon. It is joining with 3. So this is the only, we have only one shape with a pentagon. So this is a dodecahedron, a 12-face polygon. A polytope, so it's not polygon, polytope, 3D shape. This is a triangle. And for a triangle, each corner joins with 4 edges. So what is it? Very good. This is the octahedron. And finally, this is a triangle on each face, and then each corner joins with 5 edges. So each corner joins with 5 triangles. So this is a 20-faced polytope. Is that okay? So these are all the shapes that we have. Okay. Yeah. Sorry for overrunning the first class. So okay. So this is the end of this Platonic solid. So let's take a 10-minute break, and then we will come back with another result that is from the Euler planar formula. So we can prove 5-color theorem. Okay. So let's take a break.